In the name of Almighty God, I'm Master Hassan Kasha, and today I want to talk about quantum pump depletion and multi-component Schrödinger cat-like states in doubly pumped intra-resonance care microresonators. It was written by Singh, Alexandre, and Tertenkov in the independent researcher Moscow University Department of Mathematical Methods for Quantum Technologies Steklov Mathematical Institution of Russian Academy of Sciences, Moscow, Russia. We investigate quantum pump depletion and non-Gaussian state generation in doubly pumped Kerr microresonators operating in the intra-resonance regime. The pump modes are treated quantum mechanically rather than as undepleted classical amplitude, allowing pump depletion, back action, entanglement generation, quadrature fluctuations, and Wiener function negativity to emerge from the same multimode dynamics. Starting from the Kerr four-wave mixing and selection rule, we distinguish an effective resonant photon conversion model from the full Kerr Hamiltonian containing self-phase modulation (SPM), cross-phase modulation or XPM, and for wave mixing FWM. The radius model isolated the photon conversion network responsible for the discrete Zn plus one phase structure, whereas the full model retains operator-valued nonlinear Kerr phases for the n is equal to 2 intra-resonance branch. The four-mode reduced initially valued problem with the fixed coherent pump phases has a residual Z3 symmetry and generates cat-like Wiener structures near the interaction length at which the graduated mode population is maximal and the pump population is strongly depleted. The resulting states are not the canonical even or odd coherent states of Dodonov, Malkin, and Manko, but multi-component Schrödinger cat-like states characterized by vinegar negativity, non-Gaussian statistics, pump mode quadrature squeezing, and large single-mode Schmidt numbers. Comparison of the reduced and full Kerr dynamics shows the uncompensated SPM and XPM, which are self-phase modulation and cross-phase modulation. Induced phase shearing suppress the interface fringes and Wiener negativity responsible for the clear Keller's cat-like signatures. These results identify quantum depleted intra-resonance Kerr dynamics as a route to symmetry organized non-Gaussian states in Kerr resonators. Now I want to go through the introduction. Optical Kerr microresonators provide a compact platform for nonlinear optics, frequency combo generation, and quantum state engineering. In conventional Kerr comb generation, different spectral lines are associated with distinct cavity resonances separated by the free spectral range. A recently demonstrated alternative is the intra-resonance regime, where the two closely spaced pump tones drive one and the same optical resonance and generate additional frequency components inside the line width of the resonance. In this regime, the generated components are separated by subharmonics of the dual pump separation rather than by the resonator free spectral range. The classical intra-resonance comb picture predicts that when n intermediate lines are generated between two pumps, the field can possess n plus one phase stable branches. This is naturally connected with phase locking and synchronization phenomena in nonlinear dynamical systems. In the present quantum problem, the same phase locking structure appears as a discrete Zn plus 1 symmetry of the resonance photon conversion network. The symmetry fixes the number of phase-related branches, while the quantum dynamics determines whether coherent interference between these branches survives in the Schrödinger cat-like states are used for resources in continuous variable quantum information because coherent superposition of well-separated phase space components can encode bosonic qubits and protect information against specific noise channels. Their interference fringes are also sensitive to weak displacement and phase space perturbations, making squeeze cat states relevant for quantum sensing. More generally, finite superpositions of coherent states provides a standard phase space model of non-classical cat-like states. Their Wegener functions display interference fringes, photon number oscillations, and strong sensitivity to dissipation. Related depleted Palmer studies of entangled Schrödinger cat-like states in parametric down conversion have also shown that Wegener function interference squeezing Superposition statics and entanglement can coexist in fully quantum nonlinear optical dynamics. In this context, the generation of non-Gaussian catalog states inside integrated Kerr photonic platforms is of direct interest for continuous variable computation, optical qubits, and sensing protocols. For comparison, Appendix O briefly examines the undepleted pump limit where the pump modes are replaced by fixed classical amplitude. In that case, non-Gaussian states can still arise from the cubic photon conversion processes acting on the quantum generated modes, but a pump depletion, quantum backaction, and pump generated mode entanglement are absent by the construction. The central physical mechanism studied here is quantum pump depletion. In contrast to undepleted pump descriptions, the pump modes are retained as quantum harmonic oscillators. Photon conversion therefore depletes the pump sector, generates a backaction, and entangles the generated modes with the pumps. That a fully quantum treatment of the pump modes is essential for consistent description of non-Gaussian reduced state generation with pump depletion, quantum backaction, and pump generated mode entanglement. The states discussed in this work should be called Schrödinger cat-like states rather than conical even or odd coherent states. The conical even or odd coherent states introduced by Dodonov, Malkin, and Manko are characterized by Fock states. Support restricted to even or odd photon numbers. The present states don't generally possess such a strict even or odd photon number selection. Their cat-like character instead arises from multi-component phase space structure, linear negativity, and quantum interference organized by the residual Zn plus 1 symmetry. The present work is motivated in part by the n is equal to 1 quantum model of degenerate dual pump spontaneous four-wave mixing in a x to the power of 3 micro ring resonator. In that problem, the diagonal Kerr contribution can be separated by an interaction picture transformation generated by the SPM and XPM Hamiltonian. The resulting representation highlights the resonant photon conversion process while retaining the nonlinear case phases in transform form. Here we extend this viewpoint to the n is equal to 2 and n is equal to 3 interresonance branches and compare an effect photon conversion model with the full Kerr Hamiltonian containing SPM, XPM, and FWM terms. The paper is organized as follows. Section 2 introduces the multimode Kerr Hamiltonian and its explicit form mode n is equal to 2 decomposition. Section 3 explains the interaction picture separation of diagonal Kerr phases and defines Effective reduced photon conversion Hamiltonian. Section 4 derives the Zn plus 1 symmetry and the n is equal to 2 phase Lagrange equations. Section 5 lists the reduced Hamiltonians for n is equal to 1, n is equal to 2, and n is equal to 3. Section 6 defines the quantum dynamics and the normalized interaction length tau is equal to g2t. Section 7 introduces the diagnostics used as tau max. Section 8 presents the quantum depleted numerical results for the representative make modes alpha 0 and alpha 1 and compares the reduced and full Kerr models. Now I want to go through the multimode Kerr Hamiltonian. We consider an inter-resonance frequency comb generated inside a doubly pumped Kerr microresonator. The optical modes are indexed by micro is equal to 0.01 and so on until n plus 1, where the edge modes micro is equal to 0 and micro is equal to n plus 1 are externally pumped, while the intermediate modes micro is equal to 1 until the n. So they are generated through resonance four-wave mixing. The conservative multimode Kerr Hamiltonian can be written in the standard four-wave mixing form. H Kerr is equal to Hgn divided by 2 sigma lower boundaries I plus G is equal to K plus L. Alpha I, alpha J, alpha K, and alpha L. Alpha I and alpha J are positive. The selection rule I plus J is equal to K plus R expresses conservation of the frequency index in the resonant four-wave mixing. The sum runs over the order index tuples satisfying the selection rule. Hence, if the ordered constraint sum is rewritten as a sum over distinct normally ordered monomials. The monomials I plus ij plus I appears with a combinatorial multiplicity 2 minus delta ij multiplied by 2 minus delta kl. The symbol gn denotes the nonlinear coupling scale. For example, G2 is used for the n is equal to 2 branch and for defining the normalized interaction length blue. Index phase symmetry of the Kerr Hamiltonian. Consider the transformation alpha micro, which is included to e to the power of I beta micro alpha u. Each monomial transforms as alpha I plus alpha j plus alpha k alpha l, which is included to e to the power of minus I beta I, e to the power of minus I beta j, e to the power of I beta k, e to the power of I beta l, I to the power of I positive and I j positive, I k and I n, which is included to e to the power of I beta, the factorial multiplied by minus I minus j plus k plus l, I plus ij plus ik and in. Because I plus j is equal to k plus I, the phase factor is unity. Therefore, HA Kerr is invariant under the continuous index phase transformation. For the quantum initial value problem considered blue, the chosen coherent pumped phases select the residual discrete subgroup of discontinuous symmetry. Explicit n is equal to decomposition into the SPM and XPM and FWM terms. For the n is equal to 2 intra-resonance branch, the four modes are alpha 0, alpha 1, alpha 2, alpha 3, where alpha 0 and alpha 3 are the pumped modes and alpha 1 and alpha 2 are generated modes. The full Kerr Hamiltonian can be decomposed as HA or Hamiltonian Kerr to the power of n is equal to 2 is equal to HA SPM, HA plus HA XPM plus HA FWM. The cell phase modulation part is Hamiltonian SPM is equal to Hg2 divided by 2 sigma lower boundary j is equal to 0. Upper boundary is 3 ij plus and ij to the power of 2. The cross-phase modulation part is Hamiltonian xpm is equal to 2h g2 sigma a lower boundary I is greater or equal to 0. J is greater than the I and j is less than or equal to 0. 3. The photon conversion part is Hamiltonian FWM is equal to hg2 multiplied by II positive plus I0, I2 plus I2 to the power of positive 2, I1, I3 plus 2, I1 plus I2 plus I0, I3 plus HSC. The three conversion channels are the omega 0 plus omega 2 is equal to 2 omega 1 plus omega 0 is equal to 2 omega 2, omega 0 and plus omega 3 is equal to omega 1, omega 2. The factor of 2 in the non-degenerate process alpha A positive I positive 2 alpha 0 alpha 3 arises from equivalent permutation in the constraint Kerr sum. The diagonal terms Hamiltonian SPM and HXPM don't create photon in new modes, they generate intensity dependent nonlinear frequency shifts. The off-diagonal terms HFM are responsible for photon conversion, pulse depletion, and phase locking network. Thank you so much for watching my tutorial video until the end. And also, if there is any simulation for this uh, quantum pump depletion, you can download it from github.com/masterscript or github.com/CauchyScript. Today is 19th of June 2026. Time is 7:59 p.m.